So we talked about quad search trees in the previous video, but a DBMS will actually use something called a B tree, and that's just a generalization of a search tree where the branching factor is not necessarily 4 or anything really. And the B in B tree stands for balanced. So the branching factor is undefined, but it's usually very wide. Something like up to 100 can be common. Sometimes it's only maybe 10 or 15. The branching factor is determined by how many keys you can fit into a page. So depending on the size of the key, the branching factor will be either higher or lower, because you want one node to occupy an entire page. And the B there, balanced, means that these trees are always perfectly balanced. Or in other words, all of the leaf nodes are at the same depth. So it's even more balanced than an AVL tree, where some of the leaf nodes are allowed to have slightly differing depths. And we'll see how these trees are constructed later, but we don't need to do tree rotations in order to maintain this balance like we would in an AVL tree. It's just a side effect of the fundamentally different way these trees are constructed. They are kind of built from the bottom up rather than the top down in such a way that the leaves are always going to be maintained at the same level. We'll be looking at B plus trees, which are a variant of B trees with a minor difference. And many DBMSs use them, so that's what we'll be mostly focusing on, but we'll get to what that tiny difference is in a minute. So how do B plus trees work? Well, each node is now an array because we have multiple items per node instead of just one. And the internal nodes have multiple keys and multiple pointers, so they have to have a child pointer on either side of each key. And the way that what these keys mean is the pointer to the left of the key, everything in that child node is less than the key itself. So everything down here is less than E. For the pointer to the right of the key, everything in that child node is greater than or equal to the key itself. And since many of the pointers are in between two keys, just both of those rules apply. So for this branch in between E and K, everything there is greater than or equal to E and less than K. And then for the one on the far end, everything in this child is just greater than or equal to R. Now you may have noticed that every key in this internal node is repeated in the corresponding leaf node. And that is essentially the difference between a B plus tree and a B tree. In a B plus tree, the internal nodes have a different structure than the leaf nodes do. The internal nodes only hold keys and pointers to child nodes. In leaf nodes, the leaf nodes hold a key plus the corresponding data for that key. So let's look at the key E, for example. If it was not repeated in a leaf node, if the internal node only holds a key, then how do we know where that key points into the main table? Well, that's why we need to repeat it down here. So we have the key E, and then this would be the pointer into some row in the main table. In a normal B tree, we just store the information corresponding to each key right next to it. So for E, for example, the corresponding info would just be stored right there next to it inside the same internal node. And then we wouldn't need it down here taking up space in the leaf node. So why do B plus trees do this, and why do we use them? Well, because now there's this interesting property that every search key in the tree shows up in a leaf node. So the leaf nodes contain every single search key that we would ever want. Even if they're also in the internal node, they are guaranteed to be in the leaf node. More importantly, they are in left to right order. So this leftmost leaf node contains the 3 smallest items, and the one next to it contains the next 3, and the one next to it contains the next 3. And they're just, this the leaf nodes now essentially form an ordered list of all of the keys in the index. And we actually take advantage of this and we add a pointer at the end of every leaf node that points to its next sibling over. So this forms a linked list of leaf nodes that are now in sorted order. So it's kind of like we have a tree and a linked list at the very bottom levels. And the reason this is useful is because we don't always just want to search for an exact match. Sometimes we want to do a range query. So let's say we want to find everything that's greater than or equal to f. We can use the upper levels of the tree to very quickly find f within that linked list. And then to find everything greater than it, we can just start marching forward. And once we get to the end of the page, we have a link to the next page, to the next leaf node over, and we can just continue marching forward to find everything greater than or equal to f. And let's say there were more things over here, which means we would need another internal node up here and even one up here in order to make a tree. And let's say there was some key in here, I don't know, maybe pi or something. In a B tree, that key is not going to be repeated down here in the leaf node. So if I wanted to find everything greater than or equal to f in a B tree, I can't just follow this linked list. I would have to go kind of back up into the upper levels of the tree and then traverse down the other side in order to find that pi. With a B plus tree, I can essentially just ignore these other levels of the tree. Once I've found the f, I can then just use the linked list in the leaf nodes, since the leaf nodes contain every single key, and I can just march forward. Now I want to reiterate a very important property of these trees that we've been relying on, and that is that they are always perfectly balanced. So all of the leaf nodes are going to be at the exact same depth. So how do we build these trees in order to maintain that property at all times? So let's look at just a simple example. We'll use a ternary tree instead of a quad tree, just to make it simple but still interesting. And we'll insert I, J, D, and B in that order into an initially empty tree, and we'll see how the tree evolves as we add items. So we start with just an empty page, and remember a page is a node in this case. So we said that a page can hold 2 keys. The reason we know that is because it's a ternary tree, and we have 3 branches, and there are keys in between all the branches. So that means we'll have 2 keys per node. So we have our page with enough room for 2 things. Let's add I. So we can just put it there since the page has enough room for it. Now we can add J, and we have enough room for it, so we can just put it there. And we don't have any child pointers or anything like that because this is a tree, but it's a root node and a leaf node at the same time. So we don't need any pointers coming down off of it. We will add pointers and turn it into a more interesting tree as needed. So let's add the D now. We don't have enough room in this page, so we need to make a new node or a new page. Normally when you're constructing a tree, you think of when you add a new node, you go and add it as a child to some other node. But this is where the construction of a B plus tree differs. In order to maintain balance, we will add the new node as a sibling of the existing node. So that way we automatically get both leaf nodes are going to be at the same depth. So we get a new page with room for 2 keys, and so we can put the D right there. The reason we put it there instead of over here is because we need for everything in the left sibling to be less than everything in the right sibling. So that's why it went on the left. But now we don't have a tree, we just have 2 unrelated nodes. So this is where the bottom-up construction starts to become apparent. We need to add a parent to these 2 in order to make them siblings. And then we can link them up and make it into a tree. But now, what do we put into the parent? And this is where we need to pay attention to how the keys work. Everything to the left of a key in an internal node needs to be less than it, and everything to the right of a key needs to be greater than or equal to it. So we can pull up the smallest value in the right node in order to maintain that property. So we'll pull up the I. Now we can have I's left pointer going to that left node, and we can have the right pointer of I going to that node. And we have maintained the key order property. We technically have enough room for another key and another pointer here, but they're just unused for now, but there is room in that page. Okay, so now we're back to having a tree. So now let's add the B. So what we do is we start at the root node and traverse downward in order to figure out where we want the B to go. So B is less than I, so we would go to the left and decide that we want it to be somewhere in this node. The nodes have to remain ordered though, so we need to swap the D over, and then we can put the B there. And there we go. Now we have a B plus tree containing I, J, D, and B. And this is just a very simple example. There are a lot of special cases that I have intentionally avoided with this example, but we will get to those details and how to handle the special cases, including what happens when you remove an item from the tree. How do we update the tree? We'll get to all of that in the next lecture, but just to give kind of enough context for how these trees maintain balance for now. Here is what the full tree would look like if it's a ternary tree, and we're using the same insertion order from the original example we did way back where we were trying to use a binary search tree. So if we insert all the items in the same order, we'll end up with this B plus tree if it's a ternary tree. And the key here is that no matter what we're looking for, we can find anything in this tree with only 3 page accesses guaranteed, instead of relying on getting lucky with the traversal order through a binary search tree. In more general terms, though, how can we analyze the performance characteristics of a B plus tree? So let's say that the branching factor is B. So we don't know what it is, but it's going to be something large, maybe 10, maybe even 100 or something. So there are B branches per node, and there are N total nodes. Then the number of pages visited per lookup is going to be log base B of N. This is similar to a binary search tree where, let's say you have to traverse down to a leaf node, then it's going to be log base 2 of the number of nodes. That's how many steps we'll take to get down to a leaf node. And it's log base 2 because it's a binary tree and the branching factor is 2. If the branching factor is B, then it's just log base B. With a higher B, this is going to be a smaller number, some fewer steps to get down to the bottom of the tree. And that's good. That's what we want. Because remember, the performance is measured in terms of disk operations, I/O operations, not in compute. There will be slight differences in terms of the computational requirements of a B plus tree versus a binary search tree, but they're minimal anyway, and that's not what we care about. We care about I/O operations. So let's look at a few different options. If we use a B plus tree for a lookup, the number of pages, as we just saw, log base B of N. If we just did a binary search, no data structure at all other than just a sorted array of pages, then it's log base 2 of N. If we use a binary search tree, well, it kind of depends on the insertion order of the nodes. Maybe we get lucky and get some page reuse, maybe not, but it's probably going to be more on the order of log base 2 of N. So let's look at an example with some actual numbers. Let's say we have 100 million total records in the index, and this is kind of more realistic of a real actual large database. So let's say the branching factor is 100, so that means we can fit 100 keys per page. That's why the branching factor is 100. And that's just determined by the size of the key. Okay, and so that means if we have 100 keys per page and we have 100 million total records, then we will have 1 million total nodes or total pages. Okay, so with a B plus tree, log base 100 of 1 million is only 3. We can find any leaf node in 3 page accesses. With binary search, it's log base 2 of 1 million, it's about 20. With a BST, also about log base 2, so about 20. So we have done way, way better with an extremely wide balanced tree, a B plus tree, than we could do with a binary search or a binary search tree.